When you really boil it all down, chemistry is just a story about electrons, where they are, where they're going, who they're with. But what if we could actually write that story? What if we could build a superhighway for them, or even force them down a path they'd never take on their own? Well, that's exactly what electrochemistry is all about. And that gets to the heart of the matter, doesn't it? This is the fundamental question we're going to tackle today. It's really a tale of two very different but deeply connected types of chemical cells that have, no exaggeration, shaped our entire modern world. So, let's get into it. Here's our roadmap. We're going to start with a basic dance move that all electrons know. Then we'll meet our two main characters, the galvanic and the electrolytic cells. After that, we'll figure out how to measure their power, and finally, we'll see how we put them to work in our lives every single day. All right, so every good story needs a beginning, right? For electrochemistry, that beginning is always a special kind of reaction called a redox reaction. It's this fundamental exchange of electrons that makes literally everything else possible. Okay, so in this electron dance, there are two key moves you have to know: oxidation and reduction. Now, there's a super handy little mnemonic to remember this: oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. It's that simple. One atom gives an electron away, another one takes it. It's a perfect partnership. Chemists have this really clever way of thinking about these reactions. Instead of looking at the whole thing at once, they split it into two half reactions. So as you can see here, the zinc is being oxidized. See you later, 2 electrons. And at the exact same time, a copper ion is being reduced. It's happily gaining those 2 electrons. You put those two halves together, and boom, you've got the complete dance. So we've established that in some reactions, electrons are just going to move. The big question is, can we harness that natural movement? And the answer is a resounding yes. So let's meet the first hero of our story, the galvanic cell. You might also hear it called a voltaic cell. And this slide right here just nails the core idea. Look at the left image. If you just drop a zinc strip into a copper solution, yeah, the electrons transfer, but they do it directly, and all that energy is just wasted as heat. Kind of boring. But look at the right. By separating the two half reactions into their own beakers, we force those electrons to take the scenic route through that wire. And that controlled flow of electrons, my friends, that is electricity. Okay, let's break down this little power-generating machine. The electrode where oxidation happens, where the electrons leave from, that's the anode. And the electrode where reduction happens, where the electrons arrive, that's the cathode. But see that U-shaped tube in the middle? That's the salt bridge. It is the absolute unsung hero here. It lets ions flow between the beakers to keep everything electrically neutral. Without it, the whole circuit would just stop. And this is the part where it all connects back to you. That whole setup we just saw, that spontaneous flow of electrons from an anode to a cathode, that is exactly what a battery is. Every single battery you've ever used, from the one in your car to the one in your phone, is just a cleverly packaged galvanic cell. Okay, so galvanic cells are great. They harness reactions that want to happen. But what about all those chemical reactions that don't want to happen? Can we make them? Well, let's meet the second character in our tale, the electrolytic cell. This is the polar opposite of a battery. Instead of generating power, an electrolytic cell consumes power. It uses an external power source, like a battery, to literally pump electrons in the direction they would never go on their own. It forces a reaction that isn't spontaneous. Think of it like this. A battery is like water flowing downhill, doing work for us. An electrolytic cell is like using a powerful pump to force that water all the way back up the hill. This comparison table lays it all out, nice and clear. A galvanic cell, it spontaneously turns chemical energy into electrical energy. An electrolytic cell, it does the exact reverse. And get this, look at this signs for the anode and cathode. They're flipped. In an electrolytic cell, the anode is positive and the cathode is negative, all because an external power source is bossing them around. So we've been talking about electrons wanting to flow or being forced to flow, but that's kind of vague, right? How do we actually measure the strength of that push? Well, let's dive into the concept of potential and see how it all adds up. Well, that push has a name. It's called electrode potential, and we measure it in volts. It's basically just a number that tells us how badly a substance wants to gain or lose electrons compared to a universal baseline that everyone in science has agreed on. So check this out. This is the electrochemical series. And you can think of it as a power ranking for elements. The things at the very top, like lithium, have really negative potentials. That means they are terrible at gaining electrons, but they are amazing at giving them away. Then you go all the way to the bottom. You've got fluorine. It has a super positive potential, meaning it desperately wants to snatch electrons from anything it can. And here's the really cool part. If you want to predict the potential voltage of a battery, all you have to do is find your two materials on this chart. The bigger the distance between them on the chart, the more powerful the voltage you can get out of that reaction. It's like a cheat sheet for building batteries. All right, enough theory for a minute. Let's get to the really fun stuff. What incredible things can we actually do by controlling where electrons go? And the reason we can do all this is thanks to the brilliant Michael Faraday. He's the one who figured out the exact mathematical rules that connect electricity and chemistry. His laws basically give us a recipe. They tell us precisely how much electric current we need for how long to produce a specific amount of a chemical. It's chemistry by the numbers. And the applications are they're everywhere. We're talking about using electrolysis to split water to make hydrogen fuel. The entire aluminum industry, the reason we have aluminum foil in cans, is built on this. We use it to refine copper to the crazy high purity we need for electronics. And electroplating? Coating car parts with shiny chrome or jewelry with silver. All electrolysis. It is a true industrial powerhouse. Now, to describe all these different cells, chemists don't want to draw a big picture every time. So they use a clever shorthand notation that looks like this. It's like a compact map that shows you everything at a glance. The anode on the far left, the cathode on the far right, and that double line in the middle, that's our old friend, the salt bridge. So let's do a quick recap of our story so far, shall we? It all begins with that fundamental electron dance called redox. Galvanic cells, or batteries, harness the natural flow of that dance to give us electricity. Electrolytic cells use electricity to force the dance to go in reverse. And finally, electropotential is the tool we use to measure and predict it all. You know, this quote from our source material just sums up the whole thing beautifully. Electrochemistry is all about this two-way street between chemical energy and electrical energy. You can go from one to the other and back again. And that, right there, is the ultimate takeaway. The entire massive field of electrochemistry really just boils down to this one simple choice. Do we let nature do the work and give us power, or do we provide the power to make nature do our work? When you think about it, from the humble AA battery to cutting-edge hydrogen fuel cells, this science has completely defined our technological age. It's given us portable power and new materials. And it really makes you wonder, doesn't it? With our growing mastery of how to guide these electrons, what's the next incredible reaction we're going to master?